All right, welcome to our third lecture. This lecture will be covering the kind of context of solar as a systems look, and we'll discuss some of the cases, examples that are discussed in, I believe, Chapter 2 of the textbook. So, just a quick reminder, we are going to have class again on Tuesday. You have a CATME survey that has been assigned. This is a review of your teammates. That will be due on January 28th. Again, participation is mandatory in this. We do want the feedback on your teammates and on yourself and how you feel about this team development. We are trying to make a goal this semester of having interesting and rewarding team experiences that help you to really succeed in this class, in a very challenging class, and build team skills throughout the semester that are going to be crucial to your basic engineering skill set in the future. Now, I have an assignment for you. I want you to be reading Chapter 3 of Solar Energy Conversion Systems. That's the required textbook. You will see also on Angel that we have homework number 1 assigned. That is going to be coming up due, not next week, but I believe the week following that. And you will be working with your team on that assignment. Again, you can work on that in Share LaTeX. You can work on that in your desktop system version of LaTeX. Either is going to work. I just need you guys to do full attribution to each member of the team as you work through that. I'll present some great examples of people who delivered their essay reports in a really professional manner with the whole team names and the like. If you do have questions, I will be holding office hours on Mondays from 1 to 4 p.m. Welcome you to come over to the Hostler building, and I look forward to your questions, whether they are on solar or whether they are on the practicalities of Scilab or on LaTeX. Happy to help out. So get working on homework 1. It will creep up on you like you won't believe it. We have 4 homeworks. They are each of them very intense for reporting, which is part of the reason why we switched to team-based work to kind of be able to spread the load out amongst you. Now, it will be very important that you do understand all the topics from the homeworks, so you can't just divide up and not understand the concept materials. That will really get you in the end in the midterm and the second midterm exam. All right, so let's get moving forward for today's lecture. Solar is a very broad word. You tend to use the word really informally among your family members and, say, your friends. When you use the word solar, like, I'm going to go install solar on my house, you use that word to mean photovoltaics. However, in this classroom, we're really trying to expand that to the more of the broad fundamentals that make up the foundation of solar analysis for project design. And that's one of our goals, right, is to get you the skills so that you are a competent person to be developing solar projects among a team, an engineering and business team in the future. So the thing that makes solar, broadly speaking, pretty complicated is that we have all of these parts, all of these different elements that are coupled together, strongly coupled dynamic systems is what we call them, where coupling means, different parts of the system are basically married together. You can't think of them in isolation. This is not classic engineering. This is modern engineering where everything is intertwined and really dependent on each other, and it's very dynamic. It changes in time and in space, which is really in thermodynamics an open system, a dynamic open system. My 3 big systems that I'm thinking of just in terms of flows of energy and of mass are going to be the sun, big system right there, delivering a flow of photons, a flow of light that we would call shortwave radiation. And it gets delivered to the atmosphere and the Earth, not just the Earth, but the atmosphere interacting with the Earth. The atmosphere has clouds, water vapor, aerosols. All of these things interact with light and will change the trajectory of light and will cause it to reflect and refract and ultimately will reach the Earth And so we have the sun coupled to the earth. The sun is married to the earth. We have an energetic exchange between the sun and the earth, which thankfully keeps us warm. And we also then have a third system, which would be that technological system, the solar energy conversion system. SECS means solar energy conversion system. So I couple the sun to the atmosphere and earth system to the technology system. All of these guys are strongly coupled. They have parameters that are all tightly tied between mass flows, energy flows, and entropy flows. This is why I have a standard prerequisite that we really need to have a thermodynamics background to kind of get deep in the understanding of what are we talking about with solar. Now, if I were to think of that dynamic systems, what does a dynamic system mean? It's a pretty traditional concept out there in the world of science and engineering, where you're thinking of a stock, a flow with controls and feedback. So a stock, right, is anything that can be stored for a period of time. Whether the stock be financial stock, whether the stock be a stock of mass, like a lake reservoir behind a dam, or whether the stock be the sun itself. And then you have flows that are released from those stocks or that go into those stocks, and that's why I have my arrows going both ways there. And you're seeing basically different stocks that are coupled together through flows. And then on the right side, I've got a little kind of valve. That circle with an X usually symbolizes like a valve or some sort of control or some element of feedback in the flow of a system. Lots of feedbacks, lots of controls going on between the sun, the atmosphere, and the earth, and the solar technology. So we've got some pretty dynamic things happening, complicated systems, and strongly coupled systems. All these things make solar a lot more complicated than just putting a panel out on a rooftop. Now, it's not to say that that won't just work, but we're trying to start with the foundations, build from the foundations so that you have truly strong skills in your career development. Now, project development is the other aspect. So we're not just learning these things for the sake of knowing them. We really want to have fundamental knowledge so that it enables us to be strong solar project developers. As I said before, this class is not about making a new technology more efficient or finding some new technology. This is really about taking what we have and developing projects for our clients where they live. We need to anticipate the needs of our clients or our stakeholders and propose projects and develop those projects for our clients. So that's an interesting scenario then. What makes solar project development complicated? Well, solar has a long tradition of understanding that there is an ethic of sustainability going on in our motivation for developing solar. We are while a company might be very closely vested in developing solar for a financial profit, there are usually many more dimensions to developing solar than just a financial profit. I think we can't really do that anymore in any company. Sustainability is becoming a major part of the business as usual. So what is the ethics of sustainability? As we noted in the textbook, it is our relations as moral obligations. Like we have moral obligations to three different parties or three different systems of parties. First, we have in an ethics of sustainability sense, this is described very well by author Christian Becker, who is a philosopher of ethics, that we are dealing with the relations as moral obligations to contemporary people across the globe. Like, how are people related across the globe? We are now global citizens. So we have to know what are our moral obligations across the globe. What are our moral obligations to future generations? The actions that we take now, we know very clearly have an effect generations from now. And so we are making certain decisions based on that, and we are making decisions in an ethics of sustainability sense to our in relation to our supporting biome. I mean, we clearly, as human beings, as individuals on Earth, know that we're not alone. We have an entire nutritional system, entire oxygen breathing system, water, that is our supporting biome. We could not do it alone, and they cannot do it without us. So we need to have this relationship, and we need to understand how are we related. So we're talking about three different relationships with the people across the planet, the people in terms of future generations, and that biome that supports us. And that is those additional contexts beyond just financial gain are what's really making solar project development challenging, complex, very interesting, in fact, and great for career development. So the interesting thing here is that in solar, there virtually is no way to make solar turnkey, where you just drop it onto somebody's house or put it out into a field. All project solutions have a local nature, very specific to that place, that time. And all of our project solutions, again, that's the time element, are coordinated with respect to time. Time becomes very important in this class. So does the local nature of the problem. We're going to call time and space contexts, we're going to call that locale very soon. So the interesting thing is that we're always going to have uncertainty for what is going to be a best problem. I mean, a lot of you, particularly those who are gearing up for an engineering future, are used to thinking in terms of a best solution or optimal solution. Well, solar is one of those scenarios where there aren't obvious best solutions. There is usually a portfolio of solutions, and there's going to be some uncertainty around deciding for each one of those, which then tied to these relationships as moral obligations to people across the globe, to future generations, and to the supporting biome. And that means that this is a wicked problem, and that's actually something you can look up online as to what is a wicked problem. It's very a multidimensional, challenging problem. We're not talking about something being wicked as in Boston accent wicked. No, this is a challenging problem that has to be dealt with in innovative ways and creative ways. Again, making your career in solar much more interesting. Our approach to this is not that we're solving a problem. We in solar do not solve problems. We solve for pattern. There's a pattern out there in any one place that we can solve in time and space. And a lot of what we're doing when we're doing solar project development is solving for pattern. There's a really great author called Wendell Berry who talks about solving for pattern in agriculture, and that you try to solve for the pattern of the place rather than to, say, solve a single individual problem. Because what happens when you solve individual problems is you end up creating about 3 or 4 more. And that is particularly useful to think about as we move forward in solar. So, SECS's, solar energy conversion systems, are always deployed within a larger system, right? A larger system, a coupled system of the environment and society. And that, again, makes it fascinating as a topic, and it makes it something really challenging. It's really going to push you in your career as you develop. So let's think about local food systems. I use a lot of stories in my discussions with my surrounding communities, with other universities, when I go out as a guest lecturer. I want you to think about solar the way that you think about local food systems, because of course solar is food. I mean, solar is the driver for food. But let's think about local food systems, and we understand that even in local food, big energy will always have a big environmental impact. So we can't just be thinking that as solar grows, and believe me, it's going to grow, can't just be thinking that just because solar gets bigger, it's not going to have an impact on the environment and society. It will become a big energy system, and there will be challenges and complaints and political pushback even with whenever energy gets big. So keep that in mind. We'll discuss that more as the class goes on. And don't just think just because we're doing solar that we are doing the least impact environmentally. When solar gets big, it will have a big environmental impact as well. It just will be a different environmental impact than the impact of coal or the impact of natural gas and oil and so forth. So sustainable energy, though, if we were looking at this, what does that mean? I mean, we've heard of renewable energy before, but sustainable energy is really looking to additionally build in an awareness of what we would call ecosystem services and systems resilience. And there are two phrases that I really would like you to go out, do some digging around for. What are ecosystem services, and what does systems resilience mean? Right? You can kind of think of resilience as the ability to be adaptive and plastic to, or be able to bounce back from challenges. So a lot of interesting things there. Ecosystem services get divided up into 4 different chunks. We call them habitat or supporting services, provisioning services, regulating services, and cultural services. And again, rather than stopping and describing each of those, I want you to go out, dig into the web. There's something called the Millennium Ecosystems Services Report, and that really does a great job of describing these things, although the web is getting better and better at just having short descriptions for each one of these. And solar does fit in to ecosystem services. And as a matter of fact, I just came back from an entire conference on the food, water, energy nexus, where a large part of the discussions of energy and water and food were all tied to ecosystem services. So this is not some oddball topic. This is something that is becoming more and more integrated into the way that we plan and develop energy systems in society. So all of this, right, is a broader context for what are we doing in the future? How are we planning for the future? And that really, project development is planning for the future. And it all brings us back to what I would call the central goal of solar design. You'll hit a three-point target for what are we trying to do in solar design as a design team. And that is to maximize the solar utility of the resource, where utility is in economics, preference for goods and services, preference of a client or stakeholders. So solar utility then is the preference for solar goods and services. So we want to maximize the solar utility for a client or a group of stakeholders, as more and more often we find out that our clients are not individuals living in a house, but actually an entire community or an entire campus like Penn State or an entire city. So for a client or group of stakeholders, we want to maximize the solar utility. Where and when? For a given locale, in a given locale. This is where locale, again, is that space and time context going on. We use locale as a very specific word. We're going to mean it to mean both space and time. And again, it's saying that all solar is local. So again, when I'm saying locale, I could mean place, like as in the latitude, longitude. It also means the time of the day, of the year, or the time horizon. Are we doing a financial analysis for 10 years, for 15 years, for 25 years? It deals with climate regimes, basically the meteorological fingerprints of the site that you're talking about, and frequency. What is the intermittency that happens with clouds interacting with light? What is the intermittency of the diurnal cycle, the day and night cycle? As well as the context, the place and time context of social policy, code, and laws. All right? So all those things end up being part of this kind of special context that we bottle up as locale. And we're really, again, talking about pattern. Design is pattern with a purpose. Right? We're all looking to do design. We're going to spend probably the first third of this class going into the fundamentals of solar energy and the materials of solar energy that enable us to do design. But ultimately, we're doing this class to do design of solar energy conversion systems, where design is pattern with a purpose. Solving for pattern, doing it in a purposeful way, that's design. All right, so the interesting thing about the goal for solar design, it's a nice simple way of saying maximize solar utility for a client in a given locale. 1, 2, 3. Easy to remember for an exam, and great to remember when you're just sitting in a meeting amongst clients in the future, to start thinking laterally, or imaginatively, creatively, about how you could anticipate the needs of your client. But the goal will have some limits. And in that sense, sustainable patterns are coupled. There are all these different factors married together, making them wicked problems. So they don't really have maxima or optima in the way that you might think of in a simple math function. These are going to be broad functions of finding a best solution, or a highest likelihood solution among a whole portfolio of options. Just keep that in mind. But that 1, 2, 3, maximize the solar utility for a client or stakeholders in a given locale. We're going to keep coming back to that over and over again over the course of this semester. All right, frameworks. So these are like actual contexts that I think are important to kind of bring story into why solar is important, why it really is different than what you might be thinking of at first. So the first, it's all in Chapter 2, these frameworks. I present a framework first as thinking of solar as a lighting aid, right? Solar as access for visual light, where your preference for the solar good or the service is actually visual light. And this comes from a company. It's a nonprofit or a ecopreneurial venture by MIT graduate Eilek Diaz. Graduate who came from the Philippines, took an idea developed by Alfredo Moser in Brazil, a mechanic in Brazil, who had this idea of taking a 1-liter bottle of soda, clear plastic water bottle, fill it up with water, add a drop or two of chlorine into the water to make sure that nothing grows in the bottle. Chlorine doesn't do anything functionally to the solar device other than keeping it clean of growth. And then seal it up, put it into a tile of corrugated metal, much like a corrugated roof that you'd see in tropical areas. And then you can insert that unit, that 1-liter bottle unit, into the rooftop of homes. And what you've done is you've created a light tube. I mean, imagine you have small homes in tropical areas where there is no light during the daytime, or there's very little light in the depths of the room because there's no electricity for that light. Or even if electricity were available, it's too expensive. So this is a preference for a solar good and services where the preference is for lighting inside the home space, which then enables the interior to be well lit, and you don't need candles, you don't need kerosene, so all of a sudden the air quality changes and becomes better. You have more ability for reading, you have more ability for accomplishing new tasks. It's a company called 1 Liter of Light. Very interesting, very, very much worthwhile digging into and looking about to see this is solar. It's just a different story than you're used to hearing. Second one is to think about solar rights and access. This phrasing, solar rights versus solar access. Go online, look up those two terms. They have specific meaning. One is the right to actually, do something with solar energy. If I'm going outside and in some suburban areas of the United States, I do not have the right in my municipality to hang out my clothes to dry. That is a solar service, is drying your clothes. If I don't have the right to put my clothes out, then that's a challenge. I have to pay for the drying of my clothes, and I'm not getting as much of a preference out of that. Now, that's not everybody, but it's worth knowing that there are certain areas where you don't have a right to put up your photovoltaic panels. You don't have a right to put out your clothes for drying. Solar access, that's a different thing. That is actually being able to access the light that is in your area and not have it blocked from you. So the interesting thing is that in Germany, they actually have a code inside of commercial buildings. It's a code for lighting. Again, this is visual lighting, where the code is such that everybody in Germany who's working in a business building gets access to daylight. Not lighting from artificial light like many of our classrooms, but actually access to daylight. And it's really important because daylight actually increases health, it increases productivity in the business world, and that variability of the intensity of light keeps you more alert, and it actually is really refreshing. And so there's code built into German commercial buildings. Everyone gets access to visible light in the daytime. That's a fascinating development. We don't have that in the U.S. So we can be working in the center of a building with no daylight access, pretty dreary stuff, low performance in general, and oftentimes uncomfortable. So don't have it here, have it in Germany. Again, this is solar preference for goods and services. Solar power. Solar power has been around for a long time in an entrepreneurial sense, and that really goes back at least as far as our French entrepreneurs who developed solar concentrating power. And a great example is Frank Schumann from Tacony, Pennsylvania, which is really a suburb area outside of Philadelphia, where he was an entrepreneur doing concentrating solar power. This would be, he actually had great research outside in Philadelphia, where he had flat water panels. Like he had a flat panel with black tar on the bottom that he used the direct sun, like on a clear day, he'd use the direct sunlight to heat up that water and generate steam. And he later developed that kind of prototyping into mirrors, concentrating mirrors, parabolic mirrors is what we call them, to concentrate the light to generate even higher powered steam engines. And you can actually find his lab still in Philadelphia. So those of you who live in the Philly area, you look up Frank Schumann and you can find his house in the Philadelphia area and physically visit it, where he was developing solar energy back in the 1800s. The actual commercial development through British investors came about with a project that was rolled out, developed and deployed by 1911, 1912 or so in Egypt. He had a 4-horsepower steam engine pump that was used to pump water. So not to make electricity, this is using a pump to move, to have something mechanical happen. And that mechanical pumping was to pump potable water from the river into the fields, so that we have actually modern irrigation happening in Egypt. Now, the alternative was to buy coal to run a steam pump, and coal was extremely expensive, all shipped in from England at that point in time. So this was a fantastic entrepreneurial venture in the late 1800s and the early 1900s. Of course, circumvented by World War I, but fascinating stuff. You can find modern versions of solar power concentration for running a steam engine through solarfire.org. Some really great entrepreneurs, ecopreneurs who have done a lot of DIY stuff using modern techniques, and can develop tracking systems to boil water and generate steam. And I think they have some of their main heliostats inside of India right now. And of course, you've already heard the lecture before about solar ecosystem services in the Zen rock garden of Ryoan-ji outside of Kyoto, Japan, where we use the white pebbles or cobbles of rocks in the rock garden to reflect light, to be a diffuse light reflector, to penetrate light into the area where people are writing, and to also cool the adjoining airspace to the area where you are working in the so that you maintain the cool air from the night before, and then you have walls all around it that are holding it in, doing some really interesting stuff. And then the fifth one that really stands out is thinking of solar for energy independence. This was a major push in Germany in the 1970s, where Germany was finding itself seeking an independent energy strategy. A main strategy that came top down from the government was to develop nuclear power. And a method that actually worked quite well inside of France. Well, culturally, they were trying to develop some of this nuclear power right in the wine region, one of the richest wine regions of southeastern Germany, or southwestern Germany, around the city of Freiburg. And this did not go well with the farmers. The farmers did not want anything radioactive nearby their grapes. This is where you have perceived risk going on, but also a local reaction, a social reaction. And to that reaction, there were major protests from the farmers. Farmers just ended up getting arrested. And then a second protest happened when all of the students from the University of Freiburg came on down, and had a major protest with faculty and students and community members, and the police couldn't arrest them then. It was a big event. And out of that came the birth of Freiburg as a renewable energy solar city. And so Freiburg, Germany is basically one of the solar capitals of the world for solar research through the Fraunhofer Institute for Solar Energy, or Fraunhofer ISA. That is an amazing space. Been there many times. Penn State is actually a partner institution with the Freiburg University, and we know quite a few of their faculty and enjoy collaborations with them. Keep in mind that Freiburg is not an intense solar resource area. It has enough. It has more than enough. But anytime you might be thinking about solar as being insufficient, remember Freiburg, because Freiburg has not so much of a solar resource as even central Pennsylvania, but it is really booming with solar development and with opportunities inside of the solar realm. So that about concludes our lecture for today. I want to let you know where we're going to go next. We're on our way to talk about the basics, the fundamentals of radiative transfer. This is the stuff that you might find in a radiative transfer class. More than likely, you're going to encounter it for about 1, maybe 2 lectures. If you're in the undergraduate level, we're going to be spending significantly more time on it than that. And so if you don't have that background, not to worry, we will be covering it. And we call it Chapter 3, The Laws of Light. This is basically the way light works. It's not the big systems perspective, but it's understanding the fundamentals of what light is. It's going to be a lot of fun. It will be detailed, so stay tuned. And I look forward to speaking to you guys next time. Thanks so much.